All right, Chemistry 1411. This is Chapter 15, which discusses or deals with solubility and precipitation. This is the first section, section 15.1. And if you go back to your general chemistry days, your general chemistry 1 days of Chemistry 1401, you would have learned that some ionic compounds don't dissolve in water. And you would have learned the solubility table. I asked you to memorize a few of the rules way back when. And we said that when we have a compound that doesn't dissolve in water, we simply called it an insoluble compound. For example, if we have silver chloride, right? If you look at the solubility table, you see that silver chloride doesn't dissolve. That means it doesn't dissociate into its ions when it's placed in water. Again, this is what we learned in Chemistry 1401, okay? And we said that compounds that are soluble do dissociate into their ions. For example, if you think about something, I don't know, something really soluble, something like sodium nitrate, right? Sodium nitrate dissolves completely. Well, the truth about compounds like silver chloride is that in reality, that even these insoluble compounds are going to solubilize to some extent. They're going to be what we call sparingly soluble. So this is what we're going to talk about in this class. And so an equilibrium does exist between the solid, or what we can call a precipitate, the solid silver chloride, and the silver and chloride ions. Okay, so this equilibrium expression that is represented here, it says that the K is a lot less than 1. Now, why would that be? The reason why is because the equilibrium only produces a small amount of silver and chloride ions, and most of it exists as silver chloride, which is a solid, right? We see this little figure down here at the bottom, which represents the sparingly soluble aspect of silver chloride. We see the silver chloride down here as a solid, right? That's what's represented here. So we have silver chloride in the solid phase. And it's surrounded by water molecules, right? There's all these water molecules. And we see that when it's reached equilibrium, we do have some silver and chloride ions in solution, but most of what is there is still the solid silver chloride. And so if we write an equilibrium expression for the equilibrium constant, if we write K, which is going to be equal to the concentration of the silver ions times the concentration of the chloride ions, well, again, if the equilibrium lies very slightly to the side of the products, that means we're going to have really low concentrations for both our silver and chloride ions, and therefore we're going to have a really small K, right? A number that's going to be much less than 1 times another number that's much less than 1 is going to give you something a lot less than 1. So we have a really low K value for the dissolution of silver chloride. All right, so again, the reality is that if you have an ionic compound, it's going to dissolve in water and it's going to dissociate into those hydrated cations and anions. And so you should be able to take any ionic compound, like say, for example, calcium fluoride, right? And you should be able to show how it dissolves into a calcium 2+ ion. You need to know that. You need to know that the charge on a fluoride is -1 and that there's 2 of them because there's 2 fluorides for every calcium in the ionic compound calcium fluoride. Well, what happens when we reach an equilibrium is that as the concentration of the calcium and fluoride build up, what does that mean? That means the reverse reaction is going to be able to occur. So eventually you get enough calcium and fluoride ions in solution, they're going to see each other, they're going to collide with each other, and they're going to reform calcium fluoride. And that's why we write this equilibrium arrow here, okay? And we do that for compounds that are going to be slightly soluble. We don't do that for compounds that are going to be completely soluble. So it says the solution is saturated when the equilibrium here is reached and no more solid dissolves. And again, we have our expression here for our K, but we don't just simply call it K as I did over here. We actually give it a sassier name. We call it a KSP, a solubility product constant is what we call it. And the KSP, again, is going to be equal to the concentration of the ions to the power of their stoichiometric coefficients. So if we were going to write out a K expression for this reaction, or this equilibrium right here, the equilibrium of solid calcium fluoride in equilibrium with calcium ions and 2 fluoride ions, the KSP, right, the solubility product constant, would be KSP is equal to the concentration of the calcium times the concentration of the fluoride to the power of 2, or squared. Okay, and that's going to be a small number, right? Well, in order for the KSP to be valid, and this is sort of a housekeeping slide about, what are the facts on KSP, right? In order for a solubility product constant to be valid, the salts have to be only slightly soluble in water. That's something that I told you already. That's why we don't have KSP values or K values for things like sodium chloride or sodium nitrate, things that are extremely soluble. So again, slightly soluble in water. A solid that dissolves, it's got to be 100% in an ionic form. So it's got to consist of cations and anions. And the KSP value is just like any other K value that we saw in this class, that it's got a specific value at what? A specific temperature, right? Only one value at a specific temperature. So K is temperature dependent, right? I mean, you just think about dissolving, salt in water. I don't know if any of you have ever tried this before. If you make a saturated solution of sodium chloride, just table salt in water at room temperature, if you just add a little extra sodium chloride that will not dissolve, if you warm that up, it'll go into solution. So you see that temperature plays a role in equilibrium. Well, something that's going to come up over and over and over again in this chapter, especially in the first part, is molar solubility. It's the maximum amount of that sparingly soluble compound that can dissolve in a solution at a given temperature. All right. And how do we determine the solubility of the salt? Well, we evaluate the concentrations at equilibrium, right? We take a look at our KSP value, and then from the KSP, we can determine molar solubility. I just put some slides here. These are some figures that I had from a long time ago, actually teaching in a different country. But anyhow, you have a precipitation reaction here, so you can see that you have something that's obviously, if this is an aqueous, if this is water down here, you can see that whatever is being formed is sparingly soluble. You get some kind of white solid here. And then in another class I taught, we were talking about crystallization, and you can see some massive crystals here. I think this is a human being, right? So you can see that those are pretty big crystals inside a cave. Anyhow, that's for another day. We'll talk about that maybe another day. Anyhow, so how do we establish this solubility equilibrium that we're talking about, right? These KSPs, right? And I'm just talking about, just a regular old, equilibrium like this. How do we establish this? How the heck do you do it? Well, you take your sparingly soluble solid, okay, you put it in water, stir it up. That doesn't sound too difficult, okay? And eventually, it's going to become saturated with your cations and your anions, okay? It reaches its maximum solubility. Now, when you see, and this is something that I always talk about with nursing chemistry, but this is a much higher level class, but you guys get the drift, right? If I, take a solid, and let me just give you something that's completely soluble, okay? Let's say we take, and Mr. Dion is not a very good artist, okay? Let's say we take sodium chloride, right? Sodium chloride is completely soluble, and when it's in solution, you know that it makes sodium ions, right, and chloride ions, okay? So that means that in our aqueous solution, so this is supposed to be Mr. Dion's artist rendition of aqueous solution. And inside that aqueous solution, what do we have? We have sodium cations and we have chloride ions. Okay, so we'll just write a few of them in here. Now, if I add enough sodium chloride so that the solution comes completely saturated, I'm going to end up with some solid sodium chloride on the bottom, aren't I? Once I add too much, right? Once I've reached the maximum solubility, I'm going to have sodium chloride that's a solid in there. Now, it looks like to the naked eye, if you were just to leave that vessel or that beaker or cup, whatever it is, maybe a, beer glass from home or something, if you just leave that undisturbed, it looks like nothing's happening, right? You just see a pile of sodium chloride and you see, a homogeneous solution surrounding it. But the reality is this, okay? There's a dynamic equilibrium at play between that solid sodium chloride sitting at the bottom and the sodium, okay, and chloride ions. Okay? Again, it doesn't look like anything's happening to the naked eye, but there is an equilibrium that exists between the dissolved ions and the undissolved solid. Again, you don't see it, but it's happening, okay? Trust me, all right? Then we can calculate the solubility based on the KSP value, and then we're going to evaluate what's called molar solubility, which you can imagine is the number of moles per liter that are going to be soluble for our sparingly soluble compound. Anyhow, so dynamic equilibrium. Well, with all that in mind, let's take a look at a problem. And just like everything in chemistry class, it becomes more clear once you look at examples. Okay, somebody has their microphone on. If you could turn it off, that would just be great. Okay, anyhow, let's take a look. Can everybody please check? Because somebody's definitely got it on. So let's take a look at question number 1. It says the solubility of silver chloride is 1.3 times 10 to the negative 5 moles per liter, which is the same thing you know as, oops, and there you go, 1.3 times 10 to the negative 5 molar at 25 degrees Celsius, and it asks you, what's the KSP? Well, let's write out what the equilibrium would look like. We have silver chloride, which we know is a sparingly soluble compound, so it's going to be an equilibrium, right? It's going to have a low K, right? The KSP is going to be small because most of it's going to exist as solid silver chloride, but we know that a little bit, right? That's something I told you this morning. A little bit of silver ions are going to be formed, and a little bit of chloride ions are going to be formed. So initially, we're starting it with 1.3 times 10 to the negative 5 molar silver chloride. We're going to assume, even though it's a state function, that we have none of these. Then there's going to be some kind of change. Now, it tells us that the solubility of silver chloride is this. It's a really low number, right? 1.3 times 10 to the minus 5 moles per liter isn't a whole heck of a lot. So it tells you that this much silver chloride can dissolve in a liter of water at 25 degrees Celsius. So that means all of this, right? And again, it's not a lot. 1.3 times 10 to the negative 5 molar. It's not a load, okay? Is going to dissolve, right? Now, beyond that, it wouldn't dissolve, but this is how much can dissolve. So that means we're going to form 1.3 times 10 to the negative 5 molar, or moles per liter of silver ions, and 1.3 times 10 to the negative 5 molar chloride ions. So at equilibrium, we have no silver chloride. We have 1.3 times 10 to the negative 5 molar silver ions and 1.3 times 10 to the negative 5 molar chloride ions. Now, I know that probably most of you have already solved this problem already. And it's like, okay, now I can just not pay attention for a second. But hold on. I just want to be sure that you follow me on some simple things before we move ahead and it gets, more complex. And again, it's not simple, because if it was simple, anybody off the street would know this. But I want to see, does everybody follow me on just the wording of this problem? It tells you what the solubility is. Again, it's kind of things that we've looked at before, but I just want to make sure. Give me a thumbs up if you follow me on that. It's telling you that this is the solubility. Therefore, that much, at least, is going to dissolve. Or that would be the maximum. Sorry, not at least, but that would be the maximum. Okay, thanks, Katie. Good. Again, I'm not trying to boggle your mind. I just want to make sure you're with me on a Monday before, we turn up the heat here. Anyhow, now let's write an expression for our KSP. KSP, our solubility product constant, is going to be equal to the concentration of silver ions times the concentration of chloride ions, right? Because both of those are aqueous. Anything that's a solid, we do not include it. And so our KSP is going to be equal to 1.3 times 10 to the negative 5, and then we're going to square that, and we get KSP is equal to 1.7, 2 sig figs, right, times 10 to the negative 10. Can't even read that. There we go. So there's our KSP value. Give me a thumbs up if you follow me on that one. You're like, Mr. Dion, I think I could interpret that one. Write it a KSP, a solubility product expression. Okay, great. Even with our limited understanding, or just starting to look at this subject, does this KSP value make sense? Well, heck yeah. It's really small, right? KSP values are not going to be big values, right? 10 to the negative 10, that's small, my friends, okay? So not a lot of silver chloride goes into solution, but hey, we were able to determine the KSP at 25 degrees Celsius, which is pretty close to ambient temperature, depending on what your definition of ambient is, right? Anyhow, let's take a look at another one. It says here, they give you a KSP for silver bromide. They also give you the molar mass. It says calculate the KSP. Oh, no, they don't give you the KSP. It says calculate the KSP of silver bromide given that 3.375 times 10 to the negative 5 grams of silver bromide dissolves in 250 milliliters of water and forms a 250 excuse me, milliliter saturated solution. Well, let's see here. Again, it's the wording of the problem that I think is crucial here. Now, again, you might have a different opinion than me, but to me, it's telling you, give me the KSP, and it tells you that this much dissolves in that much water, okay, and it gives you a saturated solution. So it's telling you what the maximum amount of silver bromide that can dissolve is, right? Because we know that if we have our silver bromide, okay, our silver bromide is going to be in equilibrium with silver ions, right, and bromide ions. Now, based off of what we saw in the last problem, if we know the concentration of this, it's going to give you the same concentration here, right? Because the stoichiometric coefficients are all the same, right? They're all 1. Well, can we calculate the concentration of silver bromide? Heck yeah. We have the number of grams. They've given us the molar mass, so we can determine the number of moles, and we also have the volume. So I'm going to do this in one fell swoop. I don't do this a lot in this class, but you know what? This is general chemistry too, right? You know that concentration is equal to the number of moles divided by volume. So to determine the number of moles, we take 3.375 times 10 to the negative 5 grams divided by the molar mass, which is 187 grams per mole. That's going to be my numerator. Okay, and you see that grams cancel, so I'm left over with moles. And then I divide that by the volume, which is 250 milliliters. I'm going to give it 3 sig figs just for the hell of it, which would be 0.250 liters. So 0.250 liters. And we end up with the concentration of our silver bromide as being 7.22 times 10 to the negative 7 molar. All right. Now going back to our equilibrium expression, I'm going to rewrite it maybe a little neater this time. So I have my silver bromide. And again, if you can, just kind of skip ahead and say, hey, I know the stoichiometric coefficients are all 1 to 1 to 1, so I can work this out really quickly. There's no problem. If you need to make an ice table, like I'm doing, so 7.22 times 10 to the negative 7, you have none of this. Again, we assume it's a state function. We're going to lose all of this. Again, why? Because it tells you that this is your saturated solution. So you're going to lose all of that. I can put my units in here. You're going to gain 7.22 times 10 to the negative 7 moles per liter of silver ions, and 7.22 times 10 to the negative 7 moles per liter of bromide ions. At equilibrium, you've got none of the solid. You've only got silver ions and bromide ions, which have the same concentration. And so to determine your KSP, and your KSP is going to be equal to the concentration of silver ions times the concentration of bromide ions. It's going to be equal to 7.22 times 10 to the negative 7 times 7.22 times 10 to the negative 7, or square it like that. And we get that our KSP is going to be equal to 5.21 times 10 to the negative 13. There we go. So 5.21 times 10 to the negative 13. If you compare that with the KSP of our silver chloride, so the silver chloride KSP from the last problem was 1.7 times 10 to the negative 10. So if you compare these two, you can see that silver bromide is actually less soluble in water than silver chloride. Why? Because the K, or the KSP value for silver chloride, is bigger. It's still not a very big number, but it is bigger, right? It's a bigger number. And so silver bromide is going to be less soluble in water than silver chloride. Give me a thumbs up if you follow me thus far. Again, it's not supposed to be anything mind-boggling. That's not the purpose of the course. The purpose of the course is to educate, not confuse, ruin people's lives. It's just for you to learn the concepts. Okay, look at this. Just a beautiful ice table here, a little KSP work. Here, it's the exact same question. The only difference is that they want to make sure that you're still on your toes when it comes to calculating the concentration of a solution, right? Which are things that you've seen, maybe not Avogadro's number of times, but close. All right, let's try one more. Then we'll get back into some slides here. We'll talk about some concepts, and we'll talk about what's called Q or QSP. All right, it says here that the KSP value of bismuth sulfide, give you a molar mass, is 2.9 times 10 to the negative 70. Ay, 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 is that insoluble or what? That's like brick dust, you know? It's not very soluble. Calculate the solubility of bismuth sulfide in moles per liter and grams per liter. So this is essentially the molar solubility is what we're looking for. And you heard me say the word or the term molar solubility earlier on today. You know, the whole expression brick dust, you know, bricks aren't going to be very insoluble in water. That's why you can use them to construct houses and, you know, buildings, because, you know, when water falls on them, they don't dissolve, right? Well, when I was working, you know, in industry as an organic chemist for many, many years, whenever we try to crystallize a compound, you always have to put it into a solution. And anyhow, it's a long story, but whenever we couldn't get something to solubilize in the Boston, I would say, this is like brick dust, you know. All right, things that just stick with you. Okay, well, let's take a look and see if we could determine the molar solubility of bismuth sulfide. What it's asking for here in moles per liter is, right, how many moles of Bi2S3 are going to dissolve, you know, in 1 liter? Well, let me show you how you would solve this one. This one might take you a little bit of help to get started, but I think you'll follow me once I show you what to do here. So if you have your bismuth sulfide, okay, again, it's not very soluble, but we write an equilibrium and we say that we're going to produce 2 bismuth ions. Could anybody tell me what the charge on the bismuth ion would be here? Got to be Johnny on the spot with your nomenclature and polyatomic or just monatomic ions here, I guess. Could anybody tell me what the charge on the bismuth would be? It's positive. I'm asking what would be the charge? What's the quantity of charge? Definitely positive. Yeah, it's going to be bismuth 3 plus, right? These are the kind of things that you need to be aware of, right? When you see sulfide, you need to know that sulfide is S2 minus. If I have 3 of those, then I have an overall charge of -6. That means I have to have +6 over here. I've got 2 bismuths. That means that each one is going to be +3. All right, that's something that you would have looked at in General Chemistry 1, oxidation numbers, but we assume that in General Chemistry 2 that you're very quick with these, okay, that you're able to write this out very quickly, and that you can say you have 3 sulfides, there we go, like that. For example, if we go back here, if you remember the transition metals, most of them can have more than 1 oxidation state. However, we looked at silver, and silver is an exception, isn't it? Silver can only form 1 ion, and that is a silver plus ion. There are also 2 other elements that only form 1 or only have 1 oxidation state. 2 other transition metals, rather, that have only 1 oxidation state. You can maybe type them out in the chat, you know. Anyhow, so we have bismuth sulfide, and we produce 2 bismuth 3 plus ions and 3 sulfide ions. Well, initially, we're going to start out with a certain amount of our bismuth sulfide. I'm just going to call it X. You don't have to call it anything really, because the sulfide or the solid isn't going to come into play in our KSP expression. But we'll just say initially we have none of these, and then there's going to be some kind of change where we're going to lose some of that. We're going to form 2 moles of this and 3 moles of that. Right? Again, I'm going off of what? The stoichiometric coefficients. For every 1 mole of bismuth sulfide, I form 2 moles of bismuth cations and 3 moles of sulfide. So that's where these numbers 2 and 3 come from. Again, this is nothing new. We saw this in both in chapters 13 and 14, but I just want you to be fully aware of that. So equilibrium, here we have none of this. Now that's not true. You know, if you have a completely saturated or oversaturated solution, right? But anyhow, we'll just assume there's nothing left, because we're just determining the exact molar solubility, okay, of the bismuth sulfide. Then we have 2x and 3x. So watch how you would solve for the KSP, right? We know that KSP, I'm sure you could all write this out, is going to be equal to the bismuth ion squared, its concentration squared, times the concentration of the sulfide Q, right? That's our KSP expression. And so we can say that our KSP is equal to the 2x, which is the concentration of our bismuth, 2x squared times 3x to the power of 3, like that. So if you take 2 and you square it, you get 4x squared times, what's 3 times 3 times 3? 3 times 3 is 9, times 3 is 27, times 27x cubed. 4 times 27 is 108, so that's 108 x to the power of what? Who could tell me? Exactly. Thanks, Jamil. It's x to the power of 5, right? You add exponents when you're multiplying numbers. Exactly. So we get that KSP is equal to 108 times x to the power of 5. And so we know that our KSP, which is 2.9 times 10 to the negative 70, is equal to 108x to the power of 5. And so x is going to be equal to the 5th root of 2.9 times 10 to the negative 70 divided by 108. Make sure you know how to do more than just a square root on your calculator. Now I have two calculators that I routinely use when I'm teaching. The one that I'm using right now is a TI. I'm using a TI, is it? TI 30XA. Okay, this one doesn't solve polynomials. But in order to do this, the way you do it, I put in 2.9 times 10 to the negative 70 divided by 108. That gives me 2.7 times 10 to the negative 72. Now to take the 5th root on this calculator, you press second function and then you press the exponent button, which gives you a root, and then you press the number 5 and you press enter and it gives you 4.9 or 4.85, but you round it up to 4.9. So x is equal to 4.9 times 10 to the negative 15 molar. Okay, so make sure that you know how to take a cube root or a 4th root. What's another option if you're struggling with that? If you don't know how to take a 5th root, you could take 2.9 times 10 to the negative 70 divided by 108, and you could put all that to the power of 1 divided by 5, right? So 1 divided by 5 is 0.2. So if you take 2.9 times 10 to the negative 70, divide by 108, like that, and then you use the exponent button, 0.2, you end up with the exact same answer. Okay, so just a little quick math for you there. Okay, anyhow, it's asking us again for the solubility of the bismuth sulfide in moles per liter, and that is going to be our X. And so that is the maximum amount of bismuth sulfide that will dissolve. So this is the X, which is the molar solubility of our bismuth sulfide. Give me a thumbs up if you follow me on that one. Molar solubility, or solubility of the bismuth sulfide, in this case in moles per liter, is kind of the way they're framing it. Good. All right. Thanks, Joel. Good. Thanks, Shannon, Katie, Amanda. Who else is here? Violet. Good group. All right. Well, let's move on from there. First 3 questions aren't that bad, and if you're sitting here waiting, like, when does it get insanely difficult? It's not meant to be insanely difficult. It's meant to basically expand on your knowledge of equilibria. Now, you've all looked at hundreds of equilibria problems by now in chapters 13 and 14 collectively. So it's not meant to be, mind-boggling. It's just meant to just expand our definitions of, or our understanding of equilibria. Anyhow, let's talk about precipitates. Everything that we've talked about up to now, if you think about questions 1, 2, and 3, we talked about what's the maximum amount of silver chloride or silver bromide or bismuth sulfide that's going to dissolve, right? Every example dealt with the maximum amount. Well, what if you go over that, or what if you're under that amount? Well, in that case, we use what's called a reaction quotient. So follow me from the top. It says KSP values can be used to predict whether a precipitate will form or not. And for that, we use what's called a Q, which is called a reaction quotient. Now, our book uses Q and QSP, which both mean the same thing. So sometimes they call it a Q, and other times they call it a QSP. Q is the same form as KSP. The only difference is that the concentrations aren't equilibrium concentrations. That's all. Okay. So if you have an equilibrium like this, so you have strontium chromate in equilibrium with strontium ions and chromate ions. Okay, well, you could write a KSP. Well, a Q is defined the exact same way. Okay, now we saw And you're like, well, that's the exact same as the Qs that we looked at before when we compared K and Q. Yeah, absolutely. Okay, it's the same thing. Why do we leave this out? Why do we leave the strontium strontium chromate out? Is because it's a solid. Solids are not included in equilibrium expressions. All right, only aqueous ions in things that are in the gaseous phase. So there we go. The magnitude or the relative magnitude of your Q and your K is going to tell you whether precipitate's going to form or not. Now, I bet you all of you could teach this, faster than me, okay? I'm sure you all get or understand that if the Q and the K are both the same thing, they're just a product of concentrations of your ions. Well, if the Q is greater than K, then the Q exceeds the KSP, and that means that the concentration of these is too high. And then what are you going to do? You're going to push the equilibrium back in that direction, and you're going to form solid, right? So here we go. You're going to push the equilibrium back in this direction, and then you'd form a precipitate. If the Q is smaller than K, well, then in that case, the equilibrium is just going to keep pushing, moving forward, and you're going to be able to dissolve more compound. And when your Q is equal to your K, okay, you're just at the point of precipitation, okay? So when Q is equal to K, you can literally think of it as if you add one more molecule, okay, or one more formula unit of strontium chromate, and you're going to crash, or it's going to form a precipitate, okay? So just the comparison between Q and K, again, you can imagine that I'm going to ask you about this on your next exam. It's very easy for me to write a question that deals with, comparing Qs and Ks, just like we've done before. All right, so let's take a look at an example where we would compare Qs and Ks. Grab my calculator here. It says, what does it say? All kinds of stuff. It says, will a precipitate form if you mix 10 mils of a 0.1010 molar silver nitrate solution and 10 mils of a 0.0010 molar sodium chloride solution? Okay, you basically take these two homogeneous mixtures, you mix them up. Do you get a precipitate? Right? I know that many of you did experiments in General Chemistry 1 where you took two homogeneous solutions and you mixed them and you get beautiful precipitates. You made things like lead iodide, which is yellow, or you'd make, silver carbonate or whatever, and you'd look at the colors and odors, of course, and things like that. Anyhow, so we're just asking, if you mix these two homogeneous solutions, do you get a precipitate or not? Now, I didn't give myself a ton of space to solve this one, so I'm going to do kind of probably a shorter hand method of this than is in my solutions, and I haven't looked at my solutions since the holidays. So again, the solutions to all these questions are always posted to Canvas, okay, if you want to look at those. And usually in those, I give like all the dirty details. I went through and typed them all out. It took me forever. Anyhow, but I just want to see if you can follow me on this. Look, if I have 10 mils of 0.010 molar silver nitrate. Well, nitrates are soluble. So if I have silver nitrate, right, it's going to dissolve completely to give me silver ions plus nitrate ions. Now, silver ions are of interest to me because silver chloride is what I'm trying to determine if it's going to form or not. So instead of me making an ice table, I just want to do it a little bit quicker. Now look, if I have 0.01 moles per liter and I have this many milliliters, now how many liters is that? 10 milliliters is 0.01000 liters. Well, let's figure out how many moles I have. Let's see, I got 0.010 moles per liter. Again, just the concentration multiplied by the volume. That means when I start out, I've got, I put in way too many here. I should have used scientific notation, but I've got this many moles of silver nitrate. Now again, nitrates are soluble. So instead of me making an ice table, just in the interest of space, hopefully you guys understand by now that since this is completely ionic and it's going to dissolve completely, I'm going to end up with that many moles of silver ions, right? 0.010 moles of silver. Give me a thumbs up if you follow me on that concept. It's going to dissolve completely instead of me making an ice table every stinking time. Hopefully you follow me by now, and I don't mean that in a mean way, just hoping that you understand by now that if I have something that's completely ionic, it's gonna, okay, good. All right, seems like a lot of students are like, thumbs up, Mr. Dion, move on with life, buddy, come on. All right, okay, I just don't want to go too fast. I don't like going overly fast. Now look, we've also got this many moles of nitrate ions. I'm just gonna not even worry about those. Why? Because it's got nothing to do with the KSP of silver chloride. Okay, there we go. So that's how many moles of silver ions we have. Now, the KSP of my silver chloride, right, is going to be this. KSP is going to be equal to the concentration of silver ions times the concentration of chloride ions. Now, the reason I didn't write out the whole, silver chloride, is in equilibrium with silver ions and chloride ions is because we made this equilibrium expression earlier today, okay, on another question. Now, I'm looking for the concentration of my silver ions. This is the number of moles. But in order to determine the concentration, right, concentration is equal to number of moles divided by volume. So I have to divide this by the volume. Could anybody tell me what the volume would be? And it's not a trick. Hey, trick question. Could anybody tell me what the volume would be that I divide this by? Yes. Anybody else agree? All right, good. My students are saying 20 milliliters. Okay. It just breaks my heart when I see students write, well, no, it's still this concentration. No, you're adding this together with this. So now you have to divide by 0.0200 liters, and we get that the concentration of our silver ions is going to be equal to, and I have it written here, 0.0050 molar. Okay, so we've got that part down. Now we're going to do the same thing for the concentration of our chloride. So we have our sodium chloride. Again, I don't want to write out a whole ice table. I'm assuming that my students get it by now. Okay, I form sodium ions and chloride ions. I know that initially I'm starting it with 0.0010 moles per liter multiplied by my volume, which was 10 milliliters, or 0.01 liters, and I get the number of moles, which is 0.12341 moles, okay? And that means I'm going to form 0.023410 moles, okay? Again, I could have done this using scientific notation, but whatever. There we go. So to figure out the concentration of my chloride ions, again, I left out the sodium because it's not important. It's got nothing to do with what I'm looking for, so to hell with that, pardon my language. Okay, so I divide that by the total volume, 0.02000 liters, and I get the concentration of my chloride ions is going to be equal to 12350. Man, this is really carrying some serious zeros around today. Anyhow, so let's figure out what our Q is going to be. Our QSP is going to be equal to concentration of silver ions times the concentration of chloride ions, which is going to be equal to 0.0050 multiplied by 0.00050. We get that our QSP is equal to 2.5 times 10 to the negative 6. You can clearly see that QSP is greater than KSP. So will a precipitate form? Can my students answer that without me rifling back to a previous slide? Yay or nay? What's your vote? Yeah, thanks, Joel. Absolutely. Yes. Right. Since the Q is bigger, that means you've got bigger numbers here than you do when you have your KSP satisfied. And so a precipitate, we'll call it PPT, will form. What do you think? Pretty cool? Could everybody nail that one? I hope so. Yeah, good. Awesome. I think the only thing in here that I've seen students make repeated mistakes on, and it's usually people who understand the concepts, but they'll just forget to tally up, the volume. I've seen that happen many times with students, okay? All right, there we go. Oh, let's see. Skip this question. I put this question in over the holidays when I was putting these slides together. We're going to skip this one for now. I don't think I would ever ask this question on an exam. It's a pretty tough question. Anyhow, so we'll skip that one. I'd thrown it in there thinking, oh yeah, that's a good idea. And then I took a look at it. I was like, no, it's not. All right, anyhow, so let's talk about selective precipitation. I hope you guys read our textbook. I mean, it's free, good free literature. And one of the things the book goes on about a little bit is about wastewater purification. And what they have written in there about wastewater purification is really short and sweet, and it will help you understand, why do I need to know things like KSP and QSP and equilibria? They give you some good reasons. And without me going into the whole, no pun intended, the whole treatment of wastewater treatment, let's say you had two cations in a solution, okay, and you want to remove one cation and leave the other one behind. How would you do that, right? And I mean, you could do the same thing with two anions too. But let's say you've got two cations. Well, what you would do to separate them is you would add some kind of anion that's going to form a precipitate with one of them. So that means you'd have to have some kind of foreknowledge about their KSPs, but whichever one has the lower KSP is going to come out of solution first, right? And then you can just filter it off. And that's a way to separate cations. Now, let's say you had a solution of magnesium ions, okay, and sodium ions. All right, how the hell would you separate these? Well, it says here that most sodium compounds are going to be soluble in water. Okay, for example, sodium carbonate, okay, is a soluble compound in water, whereas magnesium carbonate isn't nearly as soluble. So if you were to add carbonate ions, okay, from some other source to a solution, what's going to happen? Well, the KSP of magnesium carbonate is only 6.8 times 10 to the negative 6. And so you're going to be able to remove those magnesium ions. Now, you're literally not like drawing a line between magnesium 2 plus and sodium plus, but you are physically separating those atoms from one another, okay? It's kind of a cool thing, selective precipitation. It's the kind of thing I've only ever done in my life in an education lab. I've never, been involved in any kind of, purification of cations. Not that I can think of, anyhow. Anyhow, so selective precipitation. So here's a perfectly good example. So say you've got some magnesium ions, okay? Lots of magnesium ions that are on sale, and you get some barium ions, okay? So magnesium and barium are both in group 2A. They both have a charge of 2 plus. So it's easy to compare them, and you look at their KSPs since the charge of the cations are both the same. So if you add carbonate ions slowly, in this case, again, since their charges are identical, you can just compare the KSPs. And could anybody tell me which one would precipitate first? If you just take, magnesium ions and barium ions, and you just start throwing carbonate at it, right? You just hit it with lots of carbonate ions. Does anybody have an idea which one's going to precipitate first? Sorry, I can't see your answers. There we go. Yeah, the barium is going to precipitate first because it's got a lower KSP, right? Since it's a smaller number, it's going to take less carbonate to satisfy this expression, right? You can take smaller numbers and multiply them and get a smaller number, right? If you want to get a bigger number, then you've got to take higher concentrations to multiply them. Does that make sense? Cha? No? This one would precipitate first, so it would be the barium carbonate, BaCO3. You can put here since its KSP is smaller, right? You could say here barium carbonate is less soluble than magnesium carbonate. Maybe that helps. Does that help? If I tell you that barium carbonate would be less soluble because it's got a lower KSP, yeah, okay, maybe that clears it up. Good. All right. But again, so you're like, okay, well, every time I see this question on an exam, I'll just look at the two KSPs, bada boom, bada bing, no problem. No, that's not true, okay? You can't always just compare KSP values, okay? The reason you can't always do that is because you've got to have the same cation and anion ratio. Like I already referred to that. The reason you can do that is because these are both 2+ ions. You'd also have to assume that they're in the same concentration. Okay, they both have to be the same initial concentration. Otherwise, you can't just compare KSP values. If again they have the same cation anion ratio and they have the same initial concentration, be my guest. Go ahead, just look at KSPs and you're done. But if both of these criteria have to be, or both of these must be met. If not, then you got to do a calculation. And you can imagine where I'm going with that. Yeah, I'm going to go look at example 15.11, which deals with precipitation of silver halides. This is a good question. Okay, this would be a totally, I would even put this in the vein of an ACS type question. I don't know if any of you have looked at the ACS study guide, but I would consider this like an ACS type question. It says here, you get a solution, and you've got 0.00010 moles of KBr and 0.10 moles of potassium chloride per liter. So you get this much KBr and that much KCl per liter. So you know what the concentration of each of them are, right? Because it's 1 liter, so that's pretty easy. And then you gradually add some silver nitrate. Now you know that silver nitrate is soluble, right? Nitrates are soluble. So you end up with silver ions plus nitrate ions. So now you've got a soup, right? You know that potassium chloride is soluble. You've got potassium ions plus chloride ions. You know that KBr is going to produce potassium ions plus bromide ions. And you're like, oh, jeepers, I've got way too much stuff in here. Well, hold the phone, okay? What's of interest to you? They tell you that you're going to form, you can either form solid silver bromide or silver chloride. That means it's going to be a combination of silver and bromine from the KBr and from the silver nitrate, or for the silver chloride, it would have to be silver and chloride from the potassium chloride. Okay, and you know that potassium bromide and potassium chloride are 100% ionic. So another thing that you're going to need to solve this problem are the KSPs. Now, I can't remember exactly which appendix they're in. Oh, jeepers, I forget. I think it's maybe Appendix K. Somebody might be able to correct me on that, but I think it's Appendix J. Oh, let me double check our textbook here. Appendix J. Yes, yes. Appendix J has the KSP. So if you're ever looking at a question in the book and you need a KSP and they don't give it to you, it's in Appendix J. So in Appendix J, this is one case where the appendix is not useless, right? So the Appendix J, that would only be in biology class, right? Anyhow, the appendix, or the KSP for silver chloride, KSP, I'm just writing them down here for you, is 1.6 times 10 to the negative 10. And the KSP for silver bromide is what? 5.0 times 10 to the negative 13. Now the KSP of silver bromide is lower. So that means that if you had equal concentrations of silver chloride and silver bromide, the silver bromide would precipitate first. But it's got a lower concentration, so it's not going to be that simple. So we're going to have to compare the concentration of silver ions that's required to cause precipitation in both of these cases. All right. So again, I'm not going to write out an entire ice table. I did give myself some room here, though. If we have our potassium bromide, the concentration of our potassium bromide is equal to 0.00010 molar, right? It's 1 mole, and it tells you it's per liter. So I don't know why they just didn't say molar. Who knows? Anyhow, so you've also got a concentration of potassium chloride as being 0.10 moles per liter. And what you're going to do is you're going to add silver nitrate slowly. And which one's going to form a solution first? Well, for our silver chloride, we know that our KSP is going to be equal to the concentration of silver ions times the concentration of chloride ions. Well, we know the KSP, and we know the concentration of chloride ions that we have in solution, right? Because if we have 0.01 molar KCl, again, I'm not going to write it in an ice table, but you should know that that's going to dissociate completely. The stoichiometric ratio is 1:1 for potassium chloride and chloride ions. Therefore, the concentration of my chloride is going to be 0.10 molar. So if we want to figure out what's the minimum amount of silver, or minimum concentration of silver that you would require for precipitation, we're just going to rearrange this formula to the concentration of silver ions is going to be equal to KSP divided by the concentration of my chloride ion. So my KSP for silver chloride is 1.6 times 10 to the negative 10. I divide that by the concentration of chloride, which is 0.10, and I get the minimum amount of silver ions that you'd have to put in from the silver nitrate would be 1.6 times 10 to the negative 9 molar. Okay, that's the minimum amount that you would need to cause precipitation of silver chloride. So we'll put that in a box, and now we'll do the exact same treatment for the silver bromide. So for silver bromide, the KSP is going to be equal to the concentration of silver ions times the concentration of bromide ions. If I need to know, or I want to know, the minimum amount of silver that's going to be required, I'm going to take the KSP and divide it by the concentration of bromide, like that. KSP for silver bromide is 5.0 times 10 to the negative 13. I'm going to divide that by the concentration of my bromide ions, which I get from the concentration of my KBr. Why? Because KBr is going to dissolve completely to give me, or the ions are going to separate completely to give me 1 bromide for every potassium bromide. So I have a concentration of 0.00010 molar. I'll just leave that out. And we get to the concentration of silver for precipitation of the silver bromide to occur. It's going to be 5.0 times 10 to the negative 9 molar. All right. So that means that since the concentration of silver that's required to precipitate my silver chloride is lower, okay? So what would I call this? Why don't I call this AgA, and then I'll call this one B, like that. So since, I'll write it in black. So since the concentration of silver ions required, B, is greater than concentration of silver ions in A, that means that silver chloride is going to precipitate first, okay? If you're like, I don't follow you, okay, for the very end, for the very last part, well, think about it. This is the amount of silver that you've got to have to cause precipitation of silver chloride. This is the amount of silver that you've got to have to cause precipitation of silver bromide. This number, 1.6 times 10 to the negative 9, is smaller than 5.0 times 10 to the negative 9. This is a concentration, so that means you need a lower concentration of silver ions to form solid silver chloride precipitate. Give me a thumbs up if you follow me on that one. Ja? Just kind of comparing the two KSP values and the two concentrations and figuring out what's the smallest amount of silver that I can throw in there from my silver nitrate that's going to cause some kind of precipitate to occur, right? If you started adding silver nitrate, eventually you would see something cloudy form, right? You would form a precipitate. And if you're like, what the hell is that? Well, you would do a calculation like this and you'd say, well, it's silver chloride that's being formed, right? And the silver bromide is still in solution. You can see that the numbers aren't that far apart, are they? They're not that different, but still silver chloride will form first. All righty, there we go. Okay, let's talk about the common ion effect and solubility and Le Chatelier's principle a little bit. I love Le Chatelier's principle. It comes up so much in chemistry, and it's so helpful. If you're at this point in your chemistry career, for a lot of you, this might be the last chemistry class you'll ever have to take. For many of you, you'll want to go on to organic chemistry and things of that. Le Chatelier's principle is an important enough concept to make sure you know what the heck is going on in Le Chatelier's principle. We covered it several times in this semester, but we're going to talk about it again right now. It says here what's called the common ion effect and how a common ion affects solubility. So if you have a salt that contains a common ion, so that means it's got some kind of ion that's the same as an ion that's already in solution or equilibrium. The common ion is going to affect the equilibrium position, and it's going to modify the solubility of the salt in some way. But remember, KSP doesn't change with temperature. So let's say you had this equilibrium right here. You have some solid barium sulfate that's in equilibrium with some barium ions and some sulfate ions. It says, what would the heck would you expect to happen if you were to compare the solubility of pure barium sulfate with some barium sulfate when you throw some 0.10 molar sodium sulfate into it? Well, if I think about sodium sulfate, and I think about it all the time, okay, so if I have some sodium sulfate, that means that I've got Na2SO4, okay, and it's going to solubilize to give me 2 sodium cations, okay, plus a sulfate ion, right? Well, if I throw this in here, what's it going to do to the concentration of sulfate? Sulfate would be the common ion, okay? So we'll say here, the common ion is sulfate. What's that going to do? Is that going to increase the concentration of sulfate or decrease the concentration of sulfate? And it's not a trick. If I throw a bunch of sodium sulfate into this barium sulfate at equilibrium, what's it going to do? Am I adding more salt? Right, it's going to increase. So you're going to jack up the concentration of sulfate ions. What's that going to do? It's going to push the equilibrium towards the left, okay, based on Le Chatelier's principle. And it's going to reduce the solubility of the barium sulfate because you've jacked up the concentration of sulfate just by throwing this in there. And if you're like, Mr. Dion, why do you keep leaving stuff out? Like, what about the sodium? Isn't that going to do something in there? No, right? Because sodium sulfate is a soluble compound, okay? So it's going to dissolve. Okay, the sodium ions aren't going to change diddly squat. Okay, so it's going to push the equilibrium back to the left. All right, well, let's try another problem. It's 10:32. I think we'll do this one and maybe call it a day because I think we've covered quite a bit of content. And I also want to do question 7 with you, and maybe we'll save this one for next class. So let's take a look. Question 6. Imagine yourself on the next exam, and I ask you a question like this. It says, you get a saturated solution of barium sulfate, gives you the concentration, it's really low, 3.9 times 10 to the negative 5 moles per liter. What's the molar solubility in barium sulfate, of barium sulfate when you've got it in 0.02 molar sodium sulfate? Okay, there we go. Well, the first thing we need to do here, based off of my reading on this problem, is it doesn't tell us to go to appendix, what was it, appendix K or no, appendix J. So we need to determine the KSP of the barium sulfate because it tells us you've got a saturated solution. Look, whenever they tell you the solution's saturated and they give you the concentration of something, it's kind of a wink, wink, nudge, nudge that you've got to determine KSP. So if we have barium sulfate and it's in equilibrium with barium ions, okay, plus sulfate ions, and we're starting out with 3.90 times 10 to the negative 5 moles per liter. We don't have any of these, but again, it tells you that it's saturated, so all of this is going to dissolve. Okay, what is it? Negative 5. And then at equilibrium, we don't have any of this, and then we have 3.90 times 10 to the negative 5 moles per liter, and the same concentration of sulfate. So I know you could all do this really quickly. The KSP is equal to the concentration of barium ions times the concentration of sulfate ions. You'll probably do it much faster than me. is equal to 3.90 times 10 to the negative 5 squared. And you get that KSP for your barium sulfate is 1.52 times 10 to the negative 9. There we go. So we have our KSP. Let's move on from there. Well, what the heck happens when you throw some sodium sulfate in water? Okay, if you take some sodium sulfate and you put it in water, it breaks apart to give you 2 sodium cations plus a sulfate anion. Now, if the initial concentration of sodium sulfate is 0.0200 molar, you assume you have none of these, what's the change going to be? Well, this is completely ionic. This is irreversible, so you're going to lose all of this. Right? You're going to gain 2 times 0.0200, and you're going to gain 0.0200, and then at equilibrium, you have none of this. You have 0.0400 molar sodium ions and 0.0200 molar sulfate ions. I am not a guy who skips a lot of steps, in case you didn't notice, especially as a teacher. You know, I shouldn't be skipping steps in front of my students. If you are the kind of person who's like, jeepers, creepers, Mr. Dion, that's enough, okay? I get it. I know how to do this. I know that if the concentration of sodium sulfate is 0.02, the concentration of sulfate is 0.02. If you don't have to make an ice table, be my guest. Leave it out, okay? Again, we've done it today. We've done examples where we left the ice table. If you don't need it, don't worry about it, okay? If you're the kind of person who gets tripped up on your own math like once in a while, then, you know, maybe keep going with it. So now we know that this is the concentration of the sulfate. Okay, well, again, if, let's get some more space here, if KSP for our barium sulfate is the concentration of barium ions times the concentration of sulfate ions, there we go. Well, then the concentration of barium, which is going to be the molar solubility, right? Because the relationship of barium to barium sulfate is 1:1. The concentration of barium ions is going to be equal to the KSP divided by the concentration of sulfate. There we go. Our KSP was 1.52 times 10 to the negative 9. We divide that by 0.0200, and we get the concentration of our barium 2+, which is the same thing as the molar solubility of our barium sulfate, is going to be equal to 7.6 times 10 to the negative 8 molar. Again, the reason I can say that these are equal is because the stoichiometric coefficients are 1:1. Okay, there we go, and it's a saturated solution. So there is the answer. The molar solubility of barium sulfate is 7.6 times 10 to the negative 8. Oops, I guess I could have included an extra sig fig there. Yeah, I think I could have had 3 sig figs, right? Because I have 3 here and I have 3 here. Gary, 3 everywhere else. What the heck is wrong with me? Let's see here. 1.52 times 10 to the negative 9 divided by 0.2. So I could have, yeah, 7.60. What do you know? All right, so 7.60 times 10 to the negative 8 molar, like that. All right, well, let's call it a day for there. And what I would, at a minimum, the barest minimum of bare minimums that I would like you to do by next class is to try question 7 in the exact same vein as the question that we just solved. And then on Wednesday, we're going to take a look at Lewis acids and bases and talk about how Lewis acids and bases are involved in equilibrium. We're going to look at what are called coordination complexes or complex ions. We'll talk about formation constants, or what are sometimes called stability constants. And then if there's time, we'll take a look at question 15.3. And I'd also like to take a look at some of the supplemental problems that I put in here. So I put in some additional problems. So if you want to take a look at questions 1, 2, and 3 and the additional problems, I might take a look at those as well on Wednesday with you, just to get some more practice with the first section, which is definitely the biggest section of chapter 15.